All right, welcome back. Today, we're diving into some really cool research that figured out how to make a powerful new kind of AI run up to 45 times faster. Yeah, you heard that right. So let me just start with a question for you. Imagine you've got this amazing, powerful new AI, but it's just incredibly slow. What if you could make it a jaw-dropping 45 times faster, and not by spending months retraining it, but with a single, super elegant software trick? Well, a team of researchers did exactly that.
So, what is this powerful new AI we're talking about? It's a class of models called Diffusion Large Language Models, or DLMs for short. And you should know, they represent a really promising new way to generate text. Researchers are, to put it mildly, pretty excited about them.
Now these models, they have incredible potential. They can actually match the quality of the top-tier AIs you already know, but they work in a completely different way. See, instead of just predicting the next word, one after another, they kind of refine the entire text over several steps. It's this whole iterative process that just opens up all these new possibilities that are really hard to do with standard models.
But, and this is a huge but, there was a massive problem, a giant bottleneck. The very thing that made them so special and flexible also made them painfully, cripplingly slow. I mean, so slow that using them for any real-world application was basically a non-starter. They were just stuck in the lab, a brilliant idea with no way to get out into the real world.
So, what exactly was causing this insane slowdown? Well, the problem comes down to something called the KV cache, and the ridiculously wasteful way these diffusion models were forced to handle it. The easiest way to think about the KV cache is like the model's short-term memory. As it's generating text, it stores key calculations for each word or token, so it doesn't have to start from scratch every single time. It's a pretty fundamental trick that makes most AIs fast. But for these diffusion models, that memory system was completely broken. The process was just astonishingly inefficient. At every single step, for every single new word the model generated, its entire short-term memory became just a little bit outdated. And the old solution was pure brute force. Throw the entire memory away and then rebuild it from scratch for every single word that came before it. Can you imagine an artist having to completely redraw their entire painting from a blank canvas just to change one tiny brushstroke? It was just immensely, computationally wasteful. And you don't have to take my word for it. The researchers put it perfectly themselves. This constant brute force recalculation created, and I quote, substantial latency and memory traffic. It was a massive traffic jam that was holding everything up. This was the core reason these amazing models were just stuck on the sidelines. They clearly needed a much, much smarter way.
And that smarter way? It came from a series of brilliant observations. The researchers basically acted like detectives, and they uncovered 3 key clues about how these models work on the inside. Clues nobody had really put together before.
Okay, so their first clue was all about focus. They figured out that when the model is trying to predict the next word, it's paying almost all of its attention to the words immediately around it. You know, its local neighborhood. Words from way, way back in the text, they barely have any influence at all. And that meant that constantly recalculating the memory for those distant, basically irrelevant words was just pure wasted effort.
Clue number 2 was realizing that not all the layers inside the AI's brain are created equal. You can think of the early shallow layers as handling basic stuff, like grammar and syntax. They figure things out pretty quick, and then they kind of stabilize. But the deeper layers, the ones handling more complex, abstract ideas, they keep changing, they keep updating their understanding. So, recomputing those stable, shallow layers over and over again, yep, another huge source of waste.
And this chart just shows it perfectly. Look at the changes in the shallow layers. They're minimal, right? They've pretty much settled down. But now look at the deep layers. That is where all the computational action is. The model was wasting most of its time and energy recalculating the parts that weren't even changing anymore. And this brings us to the final and maybe most crucial clue. They found a super simple, really elegant way to know when the memory was getting stale and actually needed an update. They realized that the single word, the one token the model was paying the most attention to, also happened to be the most stable. It was like a perfect low-cost anchor. If that anchor started to shift, bam, that was the ideal signal that it was time to refresh the memory. So, armed with these 3 game-changing clues, the researchers built an incredibly intelligent new strategy. They called it elastic cache.
Elastic cache is just brilliant in its simplicity. It is not a new model. It requires 0 retraining. It's basically a smart adaptive manager for that short-term memory, the KV cache. It just uses those 3 clues to make intelligent decisions about when an update is actually needed, and just as important, where in the model that update needs to happen.
This comparison just makes the difference crystal clear. The old method strategy was always update everywhere, just total brute force. But Elastic Cache's strategy, it's surgical. It asks, hey, has that most attended token, our anchor, changed much? If the answer is no, it does nothing. If it's yes, it finds the very first layer where that change happened and only updates from that layer on up, leaving all those stable, shallow layers completely untouched. Zero waste.
So, what happens when you stop wasting all that computational energy? Well, you get speed, a shocking, mind-blowing amount of speed, and you do it without sacrificing performance.
45.1 times. At its peak, on longer sequences of text, that is how much faster Elastic Cache made these models run. That is not just a small improvement, people. That is a complete and total game changer.
And here is the real kicker. You'd probably think a shortcut like this has to hurt the AI's accuracy, right? But it didn't. The performance loss was negligible. In fact, on some tasks, because the model was running so much more efficiently, the accuracy actually went up. It was faster and just as smart. How often does that happen?
I mean, the data from the paper just tells the whole story. Look at the baseline model, just chugging along at 2.6 tokens per second. A previous attempt to optimize it got it up to about 37, which is pretty good. But then you've got Elastic Cache just blowing past it at over 117 tokens per second. That's your 45x speedup. And look at that last column. It does it while matching the original model's accuracy perfectly. Just incredible.
So an achievement like this is obviously amazing for researchers, but why should the rest of us care? Because this isn't just about one specific model. It's about unlocking a whole new approach to building AI.
Here's why this really matters. This technique takes these amazing diffusion models from being a theoretical curiosity and makes them practical for real-world products. It dramatically slashes the cost and the time it takes to run them, which means a lot more developers and researchers can actually afford to play with them. It just unlocks the door for whole new kinds of applications that we couldn't even think about before because they would have been way too slow to be useful.
At the end of the day, a 45x speedup isn't just a number on a chart. It's an accelerator for innovation. It makes a powerful new technology cheaper, faster, and way more accessible for everyone. So the question is no longer if we can use these incredible new AIs. The real question now is, what are we going to build with them?